Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. And we are in section 2.1.2. We've already discussed this symbol here, which we're thinking of as a subset symbol. And we've discussed it as an existence property between two subsets or two pairs of subsets. We'll be thinking of it as a partial order now. Well, in some sense, the word partial order works really well here because take any two real numbers or integers or something like 5 and 7. I just randomly picked them, but if you think about it, they're either one is bigger than the other, or the other way around. In this case, 7 is bigger than 5, and you can do it with any two real numbers that you pick. However, you can't say, given any two sets, that one is a subset of the other, and if it's not, then it's the other way around. It doesn't quite work. For instance, let's suppose, one simple example would be if you just had one simple example would be if you just had maybe subset of 1, the subset of 2, and these are parts of or elements in the power set of 1, 2, 3. Say these are not comparable. This is not a superset of this one or a subset of that one. I mean, it doesn't work one way or the other. They're two distinct. So in fact, there's no relationship at all anyway there. So in this sense, that's why we call it a partial ordering, this symbol. So we can think of this as a kind of a ordering idea, not where one thing is a subset of something else, which is a subset of something else. So you can kind of think of this as an ordering, like a greater than or less than type symbol even. But it won't be total. It'll be partial because you can't do it between any two elements. Okay. So let's keep going here and see how we do. Okay. All right. Partial ordering. So there's some questions here that I give, and these questions actually help us know exactly what the word partial ordering means. So if A is a subset of B and B is a subset of C, then so thinking about this, so A is inside B and B is inside C, then it makes sense that A should be inside C, right? And that is true. That's actually a property that's necessary for a partial ordering, or for it to be an ordering, right? If something's smaller than something else and that thing's smaller than something else, there's going to be a transitivity idea that A will be less than C, and that's right here. So then we get that. What about, is A a subset of itself? For partial ordering, we also use that idea. It's called reflexivity. Something's always, and in a partial ordering, actually, this symbol we would say less than or equal to. Like if A is less than or equal to B, and B is less than or equal to C, then A is less than or equal to C. So you can kind of think of that. We could even write this out as so A less than or equal to B less than or equal to C. That's going to imply, I'll use that symbol. So that's going to imply that for sure A is less than or equal to C. Okay. And then here you could use this symbol. So partial ordering, usually for ordering's sake, oftentimes we use this symbol, but we could use any number of things. We could use an arrow or star or whatever else. It just has to meet these basic criteria. This first one's transitivity, this one's reflexivity, and then this one right here, if A is a subset of B and B is a subset of A, then they must be the same set. And that's definitely true with subsets, so we actually have it. So this is something that always should hold for a partial ordering. If A is less than or equal to B, and B happens to be less than or equal to A, then that's going to for sure mean that they're the same thing. Now, if you have this guarantee, it's called anti-symmetry. then we uh, have what we would consider to be a partial ordering. That's what a partial order is. A partial ordering is the introduction of a symbol, like an arrow, whatever, between pairs or between elements in a set that follow these three rules. If these three rules are obeyed, no matter what symbol you put in, it's called a partial ordering. That's the definition of a partial order. Okay, so let's keep going here. All right, so if we want to try to, okay, so for instance, if we want to try to merge 1, 2, 3, and 1, and again, as in the last example, okay. This preserves the existence of this, but it does not necessarily preserve the other properties of, partial ordering. So the merge that we had for the example before example 1, let me go up there to remind ourselves what that was. It was this one right here with all these merges that we were doing. We were taking like these two guys and putting them together into one. That merge, I guess it didn't preserve all of these properties. So these properties are like a structure, and for a function to preserve these properties from pre-image to image, from the domain to the images of what we're going to, that means that the function would preserve a partial ordering. It did preserve existence, but it's not going to preserve all of these. And here in the reading, I'm giving you an example of that. Let's see. Okay, so here's the example that I'm giving you. Okay, so remember that we have, okay. So we have, this is true, that there's an arrow relationship this way and this way, but we're also saying that they're two distinct things. That's the reason why. And anti-symmetry fails in that case. We have not preserved anti-symmetry from domain to codomain. So for instance, right here, you notice I have an arrow this way and this way, but we're also assuming that these are two distinct objects. That defies the property of anti-symmetry. Hence, this merge that we were looking at is not partial ordering preserving merge. We can just PO partial ordering. Let's shorten that to poset. Poset is another way of saying a partially ordered set. So a set with a structure of a partial order. Now, so arrow relationships, I guess, have a partial ordering, and before maybe we had a partial ordering, but afterwards, look, this is not partial ordering anymore because anti-symmetry is defied here as well as here. Okay, so partial ordering needs to be preserved if we're going to say it's a poset map or a poset or a partial ordering preserving map. Okay, so we kind of need that. All right, so here's a betweenness property for partial orders. If okay, all right, so which has to do with merges. So suppose that A and C themselves are merged together, then in order for a partial ordering to be preserved, something else has to tag along in that merge in order for it to work. B will have to merge to both of these guys, because when A and C are merged together, then there's an arrow from, then C comes over here, and that actually produces an arrow backwards from B to A and from A to B. And if they're distinct, anti-symmetry would be defied, which we don't want it to be if we want to preserve partial ordering. So the only way to make that work is we got to merge everything together here. So we'll call that the betweenness property for partial orders when we're doing merges. All right, and we want those merges to preserve the idea of being a partial order. Okay, so notice that if A and C are merged, okay. All right, so that just discusses what what we were just talking about. Okay. So for instance, yeah, okay. So this is interesting. If 1 and 1, 2, 3 are merged, since these guys are in between, everything is merging together. So really the only way to merge this one, if we're assuming that these two guys have to merge, is for them all to come together, if you're going to preserve a partial ordering. Okay, so here's just an example. The numbers are partial order, but not only they're partial order, they're actually a total order, as I was describing. Um, let's see, even just having a comma is a partial order. So I see this. So think of the comma as being like an arrow or something like that, or a greater than or less than symbol. In this particular table right here, we just partially filled it out. We didn't fill it out completely, just partially. And this is actually a partial order the way we filled it out. Notice we have reflexivity, like 1 arrow 1 or 2 arrow 2 and so forth. We also have, let's see, we also have anti-symmetry. So if it's both ways, they better be let's see, yeah. So if it's both ways, they better be the same thing. So kind of think about what we're doing. We have the set 1 through 5. That's the set we're putting the partial ordering on. And then these are just simply arrow relationships between those elements 1 through 5. Notice that that if we have 5 goes to 1, we shouldn't have 1 goes to 5, because that would mean that 1 and 5 would be the same thing. And notice we don't have 1 goes to 5. So from here to here, across the diagonal, like this guy, it's not there. If I reflect across, it's not there. That would be anti-symmetry. So this reflect across, it's not there. So anti-symmetry works as we go there. So reflexivity down the middle, and we have anti-symmetry across the diagonal. We don't see the opposite on the other side, so we have anti-symmetry. We also have transitivity. Let's see how that would work. Let's see. 5 goes to 1, 1 goes to 3. So guess what that means? Right here, 5 goes to 3. See how these colors kind of help you with that? 4 goes to 2 and 2 goes to 5. What does that mean? It means 4 will end up going to 5 here with this particular partial ordering. So this is a new ordering, not the regular ordering that we would do with real numbers or anything like that. This is a different one, but it obeys the properties of partial ordering. So we just made it up, but it obeyed the properties, so it can be termed as a partial order. Okay, so all right, and I think this is just a picture of what I was just talking about with that table, so you can take a look at that. Okay, example 4, the following is not an example of a partial order because it fails anti-symmetry. Right, and I think we've discussed that too as well. All right, well, this concludes this read along. We just completed this little subsection in the book, Discrete Perspectives in Mathematics. Thank you so much for watching.